everybody. I'm Robin Grindley. I'm also, like Pete, a product manager in the Data Center Switch Group, CSG, business unit. And I'm the manager for the Tomahawk Ultra. So this is kind of a new segment for us. First chip in a new segment really focused on extremely high performance Ethernet. Making it reliable, making it ultra low latency. And I'll show you what it does and go into a little bit of a discussion about how we got here. So we started off in 2022 and we had a vision. We said, okay, what is the market segment that we haven't really addressed with Ethernet? You know, Ethernet was now dominant in everything from Wi-Fi all the way up to hyperscalers in their cloud data centers. We said high performance computing still doesn't have or enjoy the joy of Ethernet. So we got to bring it to them. And, you know, InfiniBand was the dominant standard, is still a dominant standard. And ironically enough, when HPC started, it started with Ethernet years and years and years ago, and then realized, you know, Ethernet really just doesn't cut the mustard for high performance computing, which was unsurprising because Ethernet is and was a commodity technology. You know, it was focused on low power, low cost, not highest performance, but just getting all of the enterprises hooked up, right? And then later on moving into data centers. So it was designed for a different type of problem, different type of application. So it was unsurprising that it didn't really address high performance. So we said, okay, what are the things that really limit it for high performance, and what can we do to try and make Ethernet available for high performance and give people an alternative to a single source technology like InfiniBand? So there were a bunch of misconceptions, right? So our design team said, well, okay, what do we think, what's the limitations of Ethernet that people perceive? Well, it's high latency. Okay. They can't support very small frame sizes. You know, Ethernet frame sizes tended to be larger, right? If you had very small packets, 64 bytes is the smallest Ethernet frame size. You just can't crank that many through a switch chip. It's got some limitations there. It has a high packet overhead. You know, you're doing an Ethernet header, you're doing a TCP/IP header, you're slapping on UDP. So there's a lot of extra overhead on each packet that you send. And that's, you know, you look at the HPC world, and they're hyper-focused on getting as much payload in the packet as possible and minimizing that overhead. Ethernet is just a lossy by nature, right? And it can't really provide low end-to-end latency. So the design teams look at this and said, okay, well, none of these are fundamentally an Ethernet problem. It's just like I said, Ethernet was designed to be a certain product for a certain market segment. And there's no law that says we can't redesign the chip. Right. So in 2022, this project started. The original focus was on HPC, make Ethernet work for HPC. And the team realized that this would have to be a clean slate design. So this was not taking an Ethernet switch chip that we already had. We had, you know, Tridents and Tomahawks and Jerichos, and saying, okay, a couple minor tweaks and we'll crank out a chip. The team had to go back and say, all right, we can do this, but we're going to have to look deep in the pipeline and the way we do packet buffering, and we have to actually re-architect things. Keep it as Ethernet. That's the overall fundamental requirement. It has to stay Ethernet, but everything else we can address with re-architecting things. So the goal here was really to get Ethernet up to this level. And we actually achieved this with Tomahawk Ultra, and I'll go into some of the ways that we did this. Tomahawk Ultra is a 51.2 terabit per second switch chip. This is it. It is monolithic, which means there's no chiplets here. You mentioned, Pete, if you saw those going around, you'll notice that on this central die, you'll see on those other chips that there are little lines. That's where the different chiplets go, and then the cap goes on top. This is all one monolithic die, and this is necessary to get low latency as well as low power and get the efficiency out of it.
Who would make these, manufacture these? Are there a lot of different manufacturers who could put together something like this?
The chip itself?
Yes.
Yeah, anybody who does Ethernet switching, large silicon Ethernet switching, certainly has the capability. Like I said, there's no, we're not violating laws of physics here. We're just looking at the way that we do Ethernet switching and say, okay, let's go in there and make sure we optimize it for low latency, for high packet rates, and some of the other features that we'll show you. So anybody could do this, but we started in 2022, and it's taken us 3 years to get here. So it's not a trivial effort.
So are you fabbing these yourself?
Well, they're fabbed at TSMC.
Okay.
Yeah. I mean, we design, we fab at TSMC. And these have already shipped out to about half a dozen OEMs and ODMs, and they're building boxes. And this chip is actually 100% pin compatible with the Tomahawk 5, which is also 51.2 terabits per second. So any OEM or ODM who has a Tomahawk 5 box can actually drop this chip right onto the same PCB and start shipping a product. So they're going to come out pretty quickly. Now, so this particular implementation, this is 512 SerDes of 100 gig PAM4. Okay, so Pete mentioned earlier with the Tomahawk 6, you see two variants. There's a 100 gig PAM4 variant and there's a 200 gig PAM4 variant. So the first instance of this is 100 gig PAM4. Okay.
What is PAM4? I'm sorry.
Modulation on the wire, pulse amplitude modulation.
Okay.
With 4 bits per symbol.
Does this imply we may be seeing a 200 gig in the near future?
We have the technology. we don't pre-announce things, so I'll just say that we certainly have the technology. So performance. So if you look at historical switch chips, Tomahawk is kind of our best in class with latency. And was in the 600 to 700 nanosecond range, which is pretty good, well under microsecond. But for high performance computing, you need to get a lot lower. So we've actually achieved just under 250 nanoseconds. This is ball to ball. So the first bit in to first bit out on a packet coming through this chip. And this is independent, right? So this is a fixed latency that you can rely on. It really doesn't matter what other stuff is going through the chip. If it's all going through point to point, all crossing through the chip, you'll see 250 nanoseconds across all of these packets, okay? The packets per second, so this is kind of the horsepower of the chip. How many packets can come in and how many can you process and send out? So if you look at hyperscalers, clouds, they tend to have, on average, larger packet sizes, 400 bytes, 500 bytes. You could design the horsepower inside the chip to handle small packets, 64-byte packets. But if you did that, the cloud guys would say, well, that's cool, but I don't need it. All that means is that you're wasting silicon area and power when I'm never going to use it. So all of our chips are really designed specific to a market segment. So if you look at the other chips, they were designed with lower horsepower. It's like, if I'm not doing a Formula One race, I don't have to put a Formula One engine in this car. That's not what it's used for. It's going to Costco. Okay, well, this one isn't going to Costco. This one's going to the Formula One race. So you can see that this is 77.
Can I stop you real quick and ask a question? So just on that explanation, it's great we're using the race car to continue with the picture theme. But from a customer actually application for yours, are you looking to are you targeting customers that are primarily doing training, that are primarily doing inference? Are you targeting what size customer are you targeting? And I'd kind of be interested in that if you could talk about it.
Okay, so the packets per second here means you can handle small message sizes, which is something in the HPC world that they've always needed. That's a fundamental requirement for their shared mem and MPI type applications. In the AI world, so I mentioned we started in 2022 with this project, right? And in the fall of 2022, ChatGPT was announced. So ChatGPT comes out, now we have AI. AI kind of settled on this scale out and scale up, and everything was on training initially, right? For AI. It turned out that the AI scale up, that we'll get into a little bit more, was very similar to HPC requirements. In fact, we looked at this chip and said, well, we're already really good for AI scale up. We need to add one or two more features, and we'll kind of get into those in a minute. This chip in particular at 51.2T, you remember Pete was talking about the radix, right? You want to go collapse the network and go as big as you can for these large clusters. This chip at 51.2T has a 256 radix, and it is really optimized for scale up. So within a rack or a couple of racks, and scale up is typically where you focus on inferencing. So inferencing is very high performance. You're focused on cranking out as many tokens per second as you can, right? And it tends to be kind of optimized models that are focused on one specific area. And in that case, ultra high performance, low latency, small message sizes, high packets per second is the goal. So AI inferencing is a sweet spot, and HPC is a sweet spot for this chip. Could be used for scale out if you had a smaller cluster size. There's nothing that stops it from doing that. But typically what we see is for the large clusters, it's the Tomahawk 6s for scale out, and then the Tomahawk Ultra would be within 1 or 2 or 4 racks for scale up.
And what kind of customers are you targeting? Are you targeting kind of the Fortune 500s, Fortune 50s? Like what is your customer base look like?
So right now, scale up, as Pete mentioned, is mostly a customized solution, right? So you have people who make custom racks where they have XPU blades, they have these scale-up blades in the middle, and then they have custom copper cabling in a backplane. So these are all highly engineered bespoke solutions made by AMD, Helios, Supermicro, all of these companies that are making kind of a rack as a basic unit that has all of the scale up in it, and then it has top of rack switches that do the scale out. So initially it's for those kind of customers. Whoever needs it, whether it's pharmaceuticals or government or DOE research labs, they would go and buy these racks and systems from vendors. So we make the switch chips and we sell them to these customers who make boxes and then make rack solutions.
Got it.
Okay.
And question,
Thanks for that.
maybe you have it further in the slide as it builds out, but is some of the architecture a change on the different memory types and how much memory you put into the chip to achieve this?
Not specifically the memory types, just the way they get used.
Just the way they get used?
Right. I mean, it still has, SRAMs and TCAMs
Still
and
has
all of
SRAMs,
the
TCAMs.
standard stuff, but it's the way it gets used in the chip that is really architected for this specific use case. So performance is one area, efficiency is another. So again, we talked about, having these huge header sizes. Okay, an HPC or a scale-up network is a customized network. It's a highly managed network. It's not a general data center where anything could be swapped out, plugged in. You don't know what server you're connecting to. All these XPUs are the same. All of them are homogeneous. They are all using the same interface speeds, right? This is just the way that the network is architected. And in that case, you have complete control over every element that is connecting to those switches. So now I don't need an IPv6 address to have these two XPUs talk to each other. I know there's only 64, 128, 256 of them, whatever it is. And so I can just say, all I need is an address, 10 bits of address to address up to 1,000 XPUs, and then a little bit of extra header, but I need to keep it Ethernet. So it has to have the same SADA format with the CRC at the end. It still has to be Ethernet because it should go into any Ethernet switch, and it should get switched the right way. So within the constraint of keeping Ethernet, we can optimize these headers. And so that is supported in this chip. Specifically for scale up, AI scale up, there's this notion of in-network collectives that has been called SHARP in other implementations. And what this does is during AI, there are these collective rounds. All the XPUs do their thing. Then they all have to share data. Sometimes it's an all reduce where they share all the data and then they have to all do a computation to reduce that data and then go on to the next round of the calculation. So instead of having all the XPUs send everyone sends their piece of the overall memory space to each other, they all redo the same calculation to reduce it and then go. The switch is sitting in the middle of all of this. It can catch the data on the fly and say, hey, why don't I just do the calculation in the network itself, do all of that calculation, avoid having everybody sending data to everybody else, and then just send the result, broadcast it out to everybody. So you're offloading some computation. You'd rather have your XPUs doing real work, right? This is kind of busy work, accounting work that is necessary to get to the next stage. Why don't you offload it? Also, really, you're saving communication. You're saving a lot of bandwidth. All of these XPUs are sending data back and forth. When they don't need to, we can have the switch chip do it. So these are these in-network collectives.
You're sharing the workload across multiple GPUs, and they're trying to update each one's version of the current network or whatever layers they're working on. And you're doing some of the actual algorithm activity, computational activity in the network switch rather than having the GPUs do it. Is that what I'm
Right.
going to understand?
Right.
And how does that fit with like CUDA and all the other software that's
It's already in there. So they have a layer in CUDA where you set up a collective, like a nickel NCCL, right? What that does on their hardware is it goes up and it sets this in-network collective in the hardware in the switches, okay? And then it tells the XPUs, okay, you all are participating in this. You all have to talk to this switch to get this collective done. Exactly the same thing happens here. All of the XPUs just are going to a Tomahawk Ultra switch and saying, okay, you are doing an all reduce, you're doing an all gather. These are the XPUs that'll be sending you data. They send it, it does the computation, it sends everything back. So it's exactly the same. In fact, the CCL layer, we have a plugin that just shoves underneath there and makes it look identical. Seamless, right? What's happening under the hood is the implementation where it gets implemented, but the functionality of moving this collective into the network and saying, what is the collective? What are you doing? That is all software layer in the CCL that sets it all up.
And that's only part of Ultra, or is that part of the...
That's just in Ultra right now, right? That's a new feature in Ultra.
You would think that would be against the latency requirements. The computational activity would cost time and...
It's actually better, right? Because otherwise...
Transferring as much data?
Otherwise what you have is all of these XPUs, they all have, there's n XPUs, they all have 1/nth of the overall data set, right? They do their own thing on their own data set. Now, everyone has to send a copy to all of the other n-1 XPUs, and every XPU has to do that. So there's n times n-1 big transfers going through the network. Then every XPU gets all n chunks of data. Now it has to do a computation on all of that data, and they're all doing the same computation, right? So now you're wasting GPU cycles, all doing the same thing and then they have to wait until everybody is finished, and then there's a synchronization where they all have to say, yeah, I'm done. Okay, now we all go on to the next phase. So instead of doing that, right, there's a lot of latency waiting for that synchronization and computation. If they're all sending their chunk of the data anyway, capture it here centrally, right? So it doesn't have to go to these n-1, it goes to just one, right? It computes on the fly. As the stuff comes in, you don't have to wait for it all to come in, it does the computation, and then there's a broadcast. I'm already here at the central point in the network, boom, I send it out to everybody, and we're done. So it improves for things like MOE and some of the training, it improves latency quite a bit.
Within the rack.
Within a scale-up domain, which could be multi-rack. And then finally, in terms of reliability, HPC, and obviously this is a benefit for AI as well, has always looked at a network as a lossless fabric. We have to assume that packets get through. We can't wait, have a timer at some transport layer that waits to see few microseconds or milliseconds later, oh, I never got an ACK for this thing. I have to resend it. That's just too long. So we add features like link layer, retry, and credit-based flow control. I'll explain these a little bit more in a further section. These are new features in Tomahawk Ultra. These are also in the UEC standard, the UEC 1.0 spec. And these are optional features. right? You don't have to have these in your switch or in your XPU endpoint, but if you have them, then it makes the network more reliable and you'll get higher performance because you don't have to wait for these transporter software layer timeouts.
Those features are in the UEC1 spec.
Yeah.
And that UEC1 spec applies to some of the other Tomahawk chips, right? Are those features only available in the Tomahawk Ultra? Or what's
right
the
now
breakdown between that?
the LLR and CBFC are only in the Tomahawk Ultra right now.
Gotcha.
Other features, like the ECN and some of the things that Pete mentioned that are also in the UEC spec are in all of our chips.
Okay, gotcha.
Okay.
So it's basically breakdown of the UEC spec, then figure out which chip applies for those features.
Right. If you want the full suite right now with all of these extra features, Tomahawk Ultra is the one that has it. Okay. So again, we focused on HPC initially. So the ultra low latency, the small package handling. We also added, if you look at HPC networks, typical data center networks, cloud data center networks, they're very homogeneous, right? There may be multiple tiers, but every rack really just has n links going up, and they're all kind of the same, right? The cost of any of those links, it's the same. It's going to be 3 hops or 5 hops to get over to here. In an HPC network, it's more complex than that. They have different things like Dragonfly and Taurus, where there's this notion of there's a bunch of nodes that are they're connected very low latency locally, and then there are near nodes and there are far nodes. And if your routing can be aware of this fact and say, okay, I know this is, if I want to get over here, it's a far node, but I can hop through this other guy, then you can optimize things. So there are some other features like this topology aware routing that were added in Tomahawk Ultra, but still staying with open standards, right? Getting the cost efficiency, the power efficiency.
Question on the topology aware. So you're building a state somewhere across the fabric, right? Is that
Right.
a cluster of information that's held in its own kind of
Right. When you're doing routing, you can look at things like, okay, I have a packet that comes in and I have multiple links I know it can go out on.
Mhm.
I have alternatives. Right now it's going out on this link, but I realize in real time this link is congested.
Sure.
I'm seeing a lot of queuing on that link, so I'm going to switch it over to this other link and send it over here.
Right.
Okay.
So is that being done per Tomahawk, or is it being done across or shared information across multiple boxes?
Both.
Okay.
So it's being done in the Tomahawk. You can do it on local information. Pete mentioned this global load balancing, where
Right.
you take into account remote information as well downstream. I may say, okay, this link is really congested. This one looks better.
Mhm.
But if I go through this one, it turns out that 2 hops later, I'm going to hit another congested
So
link.
there's a sharing in the control plane of between
Right.
Tomahawks of what's happening between?
Yes,
Okay.
there's a real-time sharing. So there's inside the chip, which
Right.
is obviously hard real-time. I mean, it's gathering it at hardware speed, at line speed.
Mhm.
And then there's a control plane sharing amongst all of the switch chips as well. This
Okay.
global.
And that doesn't require anything beyond the Tomahawk. That's what's kind of what I'm getting at. It doesn't
Right.
require an extra server, state information elsewhere. It's all just direct switch to switch.
Right.
Okay.
Okay. So our goal here is really to open all of this stuff up, open standards, and make sure that we have a full ecosystem. Broadcom has always been about open standards. We don't mind competition. We're pretty confident that we can execute on a very quick cycle and have the fastest SerDes, best power, et cetera. So what we're showing here is that we've contributed this thing called Scale-Up Ethernet, this SUE. And this is just an open spec. We've actually contributed it to OCP. And all it tells you is these are the features that you should put in to get the highest level of performance from this kind of open Ethernet networking. But you can do other things as long as it's Ethernet, right? So it's an Ethernet header, and it has Ethernet features like PFC, and it's using an Ethernet PHY, then everything should plug together. There are features in UEC like LLR and CBSC. These are optional. You don't have them, it's okay. You'll still get, you plug in an endpoint, a NIC, or an XPU that has no LLR, no CBFC. You'll still get ultra low latency. You'll still get small message size performance. So it's really kind of optional how much effort you want to put into your XPU. But as long as you're adhering to these interface specs, it really doesn't matter. You'll see a discussion in the industry of UA link over Ethernet, where, yeah, the transport layer is UA link, but you encapsulate it on Ethernet, and then fine, you send it through a Tomahawk Ultra, right? Any other XPU accelerator, you can make that transport whatever you want it to be. It really doesn't matter. We have a small Ethernet header that'll get you where you need to go, and you can transport it over Ethernet, and that's really the goal. Yeah.
Up here, and you're talking about the freedom to implement however you want to in your high performance network, and you're talking, and we've been having a discussion about not just local routing but global routing and global and topology awareness, and kind of the broader discussion is how can you talk a little bit about how if I'm gonna manage this network and I'm a network engineer, how do I get my hands on to actually configure the network?
Right. So the benefit.
How does that happen?
All the standard tools. This is just an Ethernet network. It's what you're used to day in and day out. So all of the same tools that you've been using for configuration, for monitoring, they will all work, and they should work in the same way. These things just look like standard Ethernet. Now,
so do I get into this? Do I have to get into the CLI on these? Can I push automation to configure it the way I want it to? How do I,
You should not need to do anything differently. So, for example, LLR. This is something that the XPU and the switch chip will, in hardware, when you power them up, they will handshake to each other and say, can you do LLR? Yeah. Can you do LLR? Yes. Okay, it turns on. You don't need to do anything. And then it'll just run in the background. Okay. Now, if you say, I would like to gather statistics about how that LLR is running, well, those are standard APIs, Sky and Sonic and whatever you need. It's just another thing with some statistics in it if you want to gather that. But the provisioning of it and the management of it is really just happening automatically. So there's really nothing new that you have to do here.
Okay.
And that is a goal of the whole effort, is to make it standard Ethernet, standard software, standard provisioning, management, everything, the control plane, keep it the same so it looks the same, right?
And I agree with that. I like being able to have that kind of continuity, but I would push back a little bit. Even if we're just talking plain old vanilla, I'm going to move email, Ethernet. There's still some amount of configuration that needs to happen. That somehow there has to be some way to communicate with the switch to do that configuration, whether or not we're doing it, human style, or whether we're doing it by a script.
And all of those should still, if you have CLI scripts, they should still work. If you are doing it via SNMP, you should still work. If you are using Sonic, we support Sonic on all of our chips. So
you're expecting that whatever control plane Micheline is using, she's going to be able to see the switch and configure it like she would the last switch configured.
Right.
Yeah.
Yep. That is the goal.
Okay.
Cisco iOS plans.
Yeah, well, no, so
that was going to be my second question, because Sonic, I'm not even sure I know how to spell that.
Probably with a Q, maybe two Qs.
It's like the hedgehog.
YQ.
Yeah, and an umlaut over the Y.
These guys. Is there some ability to say, I don't want to run Sonic, I want to run something else?
Yeah.
Mm-hmm.
Yeah. I mean, Sonic in the hyperscaler data centers, it was started by Microsoft, right?
Oh, sure.
It was, yeah. So, I mean, it's an effort to standardize the network operating system, but it doesn't matter. From our standpoint, we have legacy compatibility back for decades, right? So any of those interfaces that you were used to using.
I'm not sure that Cisco would like to be referred to as their iOS referred to as legacy, though. So.
Yeah. Nobody wants to be old.
It worked on a 2501.
So the goal here is that if you use this scale-up Ethernet, so you have XPUs here and then going through this Tomahawk Ultra, that overall end-to-end, you can have an XPU, send out data to another XPU, and it'll be under 400 nanoseconds. So historically, we're talking about well over a microsecond, 1 to 2 microseconds of latency to get this kind of transaction done. In the new world of AI and certainly in HPC world, that was not acceptable. So we're focused on end-to-end latency here, not just the latency through the Tomahawk Ultra, which is already very low, but these endpoints need to have a very light interface that reduces the latency on the endpoints themselves.
You can come up with the wrong answer faster.
Yes, that's right. Well, yeah, but you get the wrong answer is not our problem. We're just the transport guys, right?
At least it's done fast.
We're just UPS or FedEx. We'll get your packets there on time. So
There you go.
if you look at scale up, right, the dominant one right now is NVLink. And so obviously, if we're talking about scale up, we have to look at NVLink. So in a single tier of scale up right now, current generation of NVLink goes to up to 72. As we showed with the Tomahawk 6 and the Tomahawk Ultra, you can get up to 512. So you've got a lot of roadmap there. Obviously, the bandwidth is quite a bit higher. It's 102.4 for the Tomahawk 6, 51.2T for the Tomahawk Ultra versus the shipping generation of NVLink, 28.8 tera. And then we support multi-rack. We support both scale up or scale out. It'll go either way. It's really just Ethernet. It's the way you use it. And we're really adhering to open standards. So this is part of the goal with the Tomahawk Ultra is to provide an open, completely open and standards-based approach to scale up.
Do you think you have the latency? Is your latency similar to NVLink from an XPU to XPU perspective?
Well, they don't publish numbers. So as far as we know, yes. And we released this chip in June, and we have the actual lab measurements to show sub 250 nanoseconds. I was kind of waiting personally for the announcement saying, oh yeah, but didn't see it. So as far as we know. We have different versions of this too. Some people care about highest performance. Some care about just maximum density of fitting into their XPUs. So the SUSE spec that you'll see on OCP will address both. All right, this in-network collectives, for the sake of time, I think we're kind of running short. I'm not going to go through this in too much detail, but I kind of described this verbally. You have the XPUs, they all send their data, their chunk of the data. The INC engine then does all the calculations, figures out the final result, and then broadcasts it out, right? So you're saving communication as well as offloading some of that computation from the XPUs themselves. This optimized header, if you take a standard IPv4 packet with UDP, including everything in the CRC, you're talking 46 bytes of overhead per packet. Because we can shrink this down, for the reasons I mentioned before, that we know it's a managed network, we can get this down to 10 bytes. And what this requires is the XPU has to set up that addressing scheme, tell our switch chip it's using it, and then we just route it normally. So essentially, we ignore pieces of the Ethernet address that we know aren't going to be used for this addressing scheme. And I can take questions about this afterwards if you're interested in the details, but it's still Ethernet. So it's still Ethernet. You can put one of these packets from an XPU into any other Ethernet switch, and it should work just fine.
There's a little bit of load shifting. I mean, this is happening a lot in AI, because there's a lot going on in XPU. There might be 2 or 3 chips going on here, a DPU maybe, but also just maybe a CPU head node or something like that that's handling some of this. So there's a little bit on the system architects to enable this.
Right.
Okay.
Yeah, but the switch chip can get an IP packet, and the next one is this optimized packet, and then another IP packet. This is all packet by packet on the fly, right? So the switch chip handles both. It knows what to look for. It looks at something in the header.
It does feel a little bit like that. I mean, you know, I get tired of car metaphors, but they're just so useful because there's a lot about this that you know feels like F1, which is there's, or maybe even IndyCar, which is, you know, you're just going around a loop.
Right.
There's only so much you need to do.
Yeah.
So in this case, you're asking the system vendors to sort of create that loop for you.
Is
Right.
the 250 nanosecond latency associated with the optimized Ethernet header or standard Ethernet
No,
header?
completely
Handle-
independent.
Okay.
Yeah, this is purely about payload.
And is this still working within like standard MTUs, or is there like a modified, you know, bumped up to make it supersized, like what you would think about with like jumbo frames and stuff like that go well?
We still support jumbo frames, 9K.
Okay.
Okay, the LLR quickly, what's happening here is at the link layer, right, over the wire, an error happens. Now, on the receiving end, whether it's a switch or an XPU, we have FEC, forward error correction.
Yep.
So forward error correction can correct automatically 1-bit, maybe 2-bit errors. If it cannot, what typically happens is it just drops the entire packet. So what happens here is if we find some uncorrectable error, we will actually immediately send a retry request saying, okay, you broke this packet into n subframes. The third and later subframes, you have to retransmit. So at the chip end, it has to have a small buffer to keep a packet and wait until it gets an acknowledgement saying, I got all of it. And then it releases that buffer, and then it buffers the next one.
Right.
And if it gets a retry, it says start free in and just resend free to the end.
Right.
So this is hardware that's built into the chip itself, do the link layer retry, but it happens automatically. And what the benefit here is that the upper layers never see anything. This packet that would have been lost and triggered some TCP or whatever timeout just got through. Never see it, right? So better reliability. Similarly, for the credit-based flow control, essentially you're saying that I don't want to lose drop packets because there wasn't enough buffering in my switch chip. Okay, so the switch chip, the Tomahawk Ultra, will send credits back to the sender, and it'll only send if I know there's enough space to receive that packet. And this happens link by link. Okay. All right, so this is not an end-to-end system thing. This is just the two ends say, I can do it, you can do it. Okay, we'll do this. Once the packet gets to the next link, it does the same thing. It says, okay, do you have the space available to accept this packet? And so this is all happening in hardware in real time, and you don't need any communication overhead for this. So in summary, we hit the reality with Tomahawk Ultra. We managed to achieve all of the goals. It's really an end-to-end solution for high performance, but staying within the Ethernet family. And it is shipping now. So you should see start seeing boxes coming out probably by the end of this year or early next year. So we started off with the InfiniBand vision and HPC, and now along the way we realized we can also address scale up and provide an open solution alternative to scale up. So all of these misconceptions, we managed to address all of them.